Hello. Vivek sir, good morning.
Morning, sir.
Good morning, sir. I am audible.
Yes, sir, you are audible.
Morning. So I think, sir, we should start it because time is already 9:13. Like we always start with the time. So
Okay.
good morning, participants. Again in this last day, in this 5-day FDP session 1, and yesterday we have seen and we have already announced Dr. Ojha will continue his lecture. Like yesterday, he has covered about the singular value decomposition, and continue he will touch upon the principal component analysis. So without wasting a time, I invite Dr. Ojha sir to take up the charge and take the session so that we can bind up everything in the time. So welcome you, sir, again, and please, I have already made you presenter, so I think you can, you may be able to share the screen. Thank you, sir.
Thank you, sir. Thank you. I hope my screen is visible to everyone.
Yes, sir, it is visible.
Sir, Tiwari sir.
Please.
Sir,
Yes,
there
please.
is a small window which is appearing on the center screen. Is it hiding my view, your view, or this screen?
Your screen is totally visible to us clearly. There is no obstruction.
Okay,
Totally
okay,
visible.
fine. Because I was thinking that there is a small window that is obstructing the view. Okay, fine, good. So good morning, everyone. And in continuation to yesterday's talk on SPD, singular value decomposition, that the topic we started for dimensionality reduction, I'll continue on to my next topic, that is principal component analysis. And there are several other ways in which we perform the dimensionality reduction, but actually principal component analysis and singular value decomposition, these are the two most famous techniques for dimensionality reduction in machine learning. Principal component analysis has been used for several other applications as well. So in that regard, principal component analysis becomes a very important algorithm, not only in terms of dimensionality reduction, but in terms of other classification algorithms as well. And sometimes it is also taken help of principal component analysis in case of clustering, because we are actually projecting our data onto another dimension. Okay. So principal component analysis is a statistical procedure that uses the orthogonal transformation to convert a set of observations of possibly correlated variable into a set of values of linearly uncorrelated variable that are called principal component. So our idea is we have a set of data and we want to convert this set of data into another projection. Like yesterday also I talked about a projection in which we have our data. So in support singular value decomposition, when I talked about that transformation at the end, I told you that we multiply the original matrix data matrix A with V transpose. So V transpose we had already calculated in the last class, and that projection, when we multiply A with V transpose, that is a kind of projection we are obtaining. We are projecting our data onto another dimension. So this dimensional space is a smaller dimensional space, and when we project our data into a new dimensional space, we get a smaller number of dimensions. However, data remains same. Okay, so data remains same. Like take this example, suppose I could annotate, and if I have a vector, I want this vector to be projected onto x and y axis. Okay, so x-axis projection will be something like this. We will have x value over here. So I have a vector like this, and I want it to be projected onto x-axis. So x-axis will be projected here, and on y-axis it will be projected here. So I'll have y value, I'll have x value. Okay. So in this way, we get the projection of this vector onto different axes. So this is a projection onto higher dimension. However, what we do in principal component analysis or singular value decomposition is to get a projection onto a lower dimensional space. Okay. And how do we obtain these lower dimensional space? That is what we are going to study in this lecture. And one more thing, correlation plays a very important factor over here. When we talk about principal component analysis, first of all, we have to understand that our data is highly correlated. Okay. Whenever we obtain a feature explaining some data point, we all understand that all the data points explain, all the features explain a single data point. So suppose you have to explain a person like Munindra Oja, then every feature is actually talking about Munindra Oja. So in that case, what happens is that all the features are very correlated. So suppose I have to explain someone else like Dr. Vivek Tiwari, then all the features that are being explained are very correlated because they are all again talking about Dr. Tiwari only. So in a way, these data points represent human being, human male. So if all these data points are representing a human male, then what happens that many of the features that we actually include in our data are correlated. When they are correlated, they create a lot of problems. First problem is that redundancy issue comes. So when it is redundancy, it means you have a person's height and weight, and suppose these two things are there, so with these two things we can explain a person. But take another example in which let's say I say that how many kilometers a person walked in a day. If I explain this thing and I add another feature in which I explain how many calories burned for that day, so these two features are very correlated because the number of kilometers you ran a day versus the number of calories are, they are directly proportional. So having these two type of feature in the data is not very useful. So we can safely drop similar feature which are related, very closely related with one of the other existing features. So you can choose which feature to drop, and you can drop like number of kilometers ran and number of calories dropped. So number of calories dropped probably can be, this feature can be dropped out. However, there are some features which you cannot find direct correlation, and you don't understand, we can't understand that how to find direct correlation. So in those cases, what we do, we take the help of covariance matrix, and then we try to find out the relation between these features. And then when we perform principal component analysis, we try to find out those features which are not at all related. They are totally independent. Okay, that is why we transform them into a set of values of linearly uncorrelated variables, and those variables will be called principal components. Okay, and in this process we drop so many principal components which are not so significant, and then we try to obtain an approximate data which is kind of a very close approximation of the original data, and this way we reduce, we shrink, we find the summary of our original data. Now, what are principal components? This, whenever we talk about principal component analysis, as the name suggests, it is analysis of principal components. So, what are principal components? A principal component is a linear combination of original values. Okay. First of all, this thing should be very clear in everybody's mind that principal component is nothing but a linear combination of existing features. Okay, so we have existing features with us, we try to find a linear combination, and then those linear combinations are called principal component. But when we find a linear combination, it's kind of a weighted sum of weighted combination of existing features, then those finding those weights, multiplying these weight values with the feature, and then adding them together to find the linear combination is the trick applied over here. but every principal component is a linear combination of existing original values. Principal components are extracted in such a way that the first principal component explains maximum variance in the data. Okay, I think I should highlight this point, the maximum variance. So first principal component explains maximum variance in the data set. This term carries a lot of significance. When I will go through this lecture, you will come to understand why I'm always talking about explains maximum variance. So first principal component explains maximum variance in the data set. The second principal component tries to explain the remaining variance. Okay, so there is a variance in the data set. So variance of whole data set, whole matrix can be calculated. But let's say the first principal component explains 60% of the variance. Explain 60% of the variance means it actually identifies why we have this variance. So that is so first principal component is the reason. It is the reason why this variance up to 60% of variance is because of the first principal component. Then second principal component tries to explain the remaining portion of the variance. So suppose 61% is explained by first principal component, then 40% will be explained by the second. It will try. But then second, third will try to achieve the remaining principal component, and then fourth, and then so on, so forth. It goes on like that. So second principal component tries to explain the remaining variance in the dataset and is uncorrelated to the first principal component. Actually, they are perpendicular to each other. Third principal component tries to explain the variance in which is not explained by the first two principal component. And again, the third principal component is again perpendicular orthogonal to the first two principal components. Okay. So in that regard, you understand that first principal component becomes one axis, second principal component becomes second axis, third principal component becomes third axis, because all of them are perpendicular to each other. Then these three we can visualize in space, because we are limited by our visualization of three-dimensional spaces only. Suppose we can visualize a four-dimensional space, then fourth principal component will be a component which will in four-dimensional space be perpendicular to all these three. Okay, so I am not um, expert in identifying what would be the four-dimensional space, but if suppose you have the imagination, you can imagine what would be the four-dimensional space. Then in that case, what I'm trying to say over here is that since first component explains the maximum variance, the second component would be parallel to that, perpendicular to that. Okay, just like we have two-dimensional axis. So we have one axis, that becomes our first principal component, then second axis which is perpendicular to the first one, so that is independent. Okay, try to understand this term, the independent. They are linearly uncorrelated, so they are independent to each other. So when two components are perpendicular to each other, when I find the third principal component, that is the third dimension, you say the third axis which is perpendicular to both of these two existing first and second. Then if I can find the fourth dimension, I can visualize the fourth dimension. The fourth principal component will be perpendicular to all three of them. Okay. So when should I use PCA? When you want to reduce the number of variable, of course, we are trying to reduce the dimensionality, but aren't able to identify variable to completely remove from consideration. The example that I gave you, the number of kilometers you ran today versus the calories, these two examples we were very easily able to identify whether they have a correlation or not, and we directly found that they are directly proportional, and we were able to identify the correlation, a strong correlation between them. So we were able to identify a feature and we were able to remove that. But suppose there are two feature, height and weight, and within height and weight I'm not able to exactly find out the correlation and I'm not able to remove them, then in those scenario PCA comes very handy. When you want to ensure your variables are independent of one another, so ultimately the projection on next dimensional space make all the variables independent of each other. When you are comfortable making your independent variables less interpretable. Less interpretable means when we have the data, by just looking at the data, sometimes we are able to uniquely identify the property of the data or the property of the space. Um, like you say, if the feature is gender, okay, if the feature is gender, there are two possibilities, male and female. These kind of data is with you. So we have male and we have female. As soon as we look at the data, we immediately understand what this data point represents. Okay. However, if you're comfortable with this transformations, that I transform the male and female value, like if it is male, suppose it is 0 and female is 1, so 0 1 0 1. So still 0 1 0 1, we understand that okay, it could be male female, but I transform this 0 1 into some kind of other type of numerical value in which it is 0.234 and something like that. And this transformation is not a unique representation of 0101, but a linear combination of several other feature values. Okay, so I get, instead of gender being 0 or 1 or male or female, I get a transformation, and in that transformation the feature x, this will not have any name. This feature x will have some value 0.1 0.2 0.3 something like that. And this transformation will not immediately tell you what would be the gender of the person or how uniquely you could represent that data point. So in such kind of scenario in which you are comfortable with this transformation, because this transformation is going to happen, your data is not going to remain same or not going to remain as interpretable as it was previously. Like immediately male female you are able to identify, and now these numerical values you will not be able to uniquely identify the property. If you are comfortable with this transformation, then PCA, you should go for PCA. Okay, so let's take this example in which in the following figure our data contains two features, x1 and x2. Looking at the visualization, it should be clear that observations are spread out like an ellipse with a lot of length and very little height, like this example you see. So this is the data, and when we plot this data on x1 and x2 axis with the help of x1 x2 axis, we say that our data is spread in this fashion, So first principal component actually explains the maximum variance. Okay, so this principal component, we need to find a linear combination of all these data points such that its first principal component is kind of a straight line, or later I will tell you that this is very closely related to linear regression as well. That this is the first principal component is the linear regression line on which all these data points are projected. These data, you see these gray points are data points, right? But the black line is the regression line on which all these data points are projected. How projected? Such that this line actually represents the maximum variance. So starting from lowest edge to highest edge. So this maximum variance is explained by this line, and this line becomes the first principal component. It explains the maximum variance. Then second will be perpendicular to this in the direction which explains the remaining maximum variance. So first principal component explains the first maximum variance, second principal component explains the second maximum variance, and so on. So looking at the visualization, it should be clear that observations are spread out like an ellipse with a lot of length and very little height. A casual statement says we can say that variance of the length is significantly greater than its height. Instead of calling length and height, let us refer to our technical term. The direction with the most variance is the first principal component, and the direction with the second most variance is the second principal component, and this goes on with the third principal component, fourth principal component, and so on. So the direction with the most variance as the first principal component. So what we are going to use from now on, instead of calling length and height, let us refer to the direction. So what I'm going to call this principal component as the direction. Okay, the direction in which we obtain the maximum variance. The direction in which you obtain the second maximum variance is the second principal component. How does PCA work? We provide a brief summary, and first what we do, we calculate a matrix that summarizes how all variables relate to each other. Okay, then break this matrix down into two separate components, or direction and magnitude. So first of all, we create a matrix that summarizes how all variables relate to one another. So we are trying to find a covariance matrix over here. Then second step would be to break this matrix down into two separate components. The first component would be direction, second component would be magnitude. Now we transform the original data to align with these important direction. Okay, so first of all, we find out the direction. In the second step, the first thing what we find out is direction, right? When we find out direction, we transform our original data to align with these important directions. We transform the original data to align with these important directions. The important direction, remember the important direction again, the direction with the most variance is first principal component, direction with second most is the second principal component. And from here I am taking the term direction, and I'll always be talking about in terms of direction. So when I have the first matrix, we calculate a matrix that summarizes all variables related to each other. Then we break it down into direction and magnitude. We take the most important direction, transform the original data to align with these important direction, which are nothing but a combination of our original variable. Okay, yes, these are combination of our original variable, the linear combination of our original variable. Now think about a case where data has more dimensions. By identifying which direction are most important, we can project our data onto a smaller space by dropping some directions that are least important. Okay, so what we do over here, this is the overall algorithm brief summary in which we project our data into new dimensional space. From new dimensional space, we identify which direction is most important. Then we gradually sort these in the order of important direction. Okay, the order of magnitude we sort it in the decreasing order. So this magnitude identifies which direction is the most important direction. The greater the magnitude, the greater more important the direction is. So we first calculate the matrix which tells us how all variables are related to each other. Then we break them down into two components, magnitude and direction. Depending upon magnitude, the decreasing order of magnitude, we find out which directions are the most important and we transform our original data into these directions. When we have done that, then we identify which directions are least important and we drop those directions. When we drop those directions, it means we are dropping those dimensions. With the direction, you can easily understand that in this axis, x1 and x2 are two directions. Okay, their direction or their dimension, they are basically same thing. So if I drop x2, I am left with one dimension only, and with one dimension I can reduce the dimensionality of my data. So suppose you have projected your data, you had first originally 100 feature values. Okay, so in your data matrix you have 100 feature values. The number of principal component that will be created will again be 100 only. The principal component that will be created will again be 100. But out of those 100, you can very easily identify which principal component will not have a very significant value, I mean least significant value, and then you can drop those. So out of 100, you can drop 70, 80 principal components which will have a very insignificant value. So if you suppose out of 100 you dropped 70-80% of directions, then you have dropped 70-80% of dimensions. So what you are left with is 20 or 30 feature values. So that's a huge gain in terms of the dimensionality reduction. Okay. Right. So in this algorithmic view, let us take a walkthrough on PCA and try to understand what are the steps with which we implement PCA. First of all, we need to organize our data matrix. So the first step that was given over here, we have to calculate a matrix that summarizes how all variables relate to one another. So in this step, the first step is uh, organize the data matrix. When we organize the data matrix, we need to have a tabular data. Okay, that is the precondition. Again, this precondition comes from for the SVD, it comes for PCA. So when I say that you visualize your data as data of rows and columns, the premise of that is that we have to implement these algorithms, statistical algorithms, singular value decomposition and principal component analysis, and a lot of dimensionality reduction algorithms actually visualize data as data of row and columns. So even text data we convert into data of rows and columns, and we get a numerical vector out of every document that we have. So we have a tabular data which is organized with n rows and d columns corresponding to input variables, the matrix of which is, we will denote this matrix as matrix X. Okay, because this is the set of input values we have, and we always denote input values with the symbol X. So first step is to have a tabular data organized with n rows and d columns. Okay, so with these metrics, now let us try to find the center the data matrix. When we center the data matrix, what do we mean? To ensure that each column has a mean 0 for each column. Subtract, and how do we do that? We subtract the mean of that column from each entry. So we are trying to center the data matrix. When we center the data matrix, I'm not centering the whole matrix as one center. I'm centering every column. Okay. So what we do, for every column, we find out the mean value, and then we subtract the mean value from this, from each data point. So suppose I have a set of data point in a vector, set of data points in a vector, like suppose these are the columns, these are the rows. So in every column, okay, we find out the mean value. So let's suppose mean value of this column is m1, then x1. When I find the mean value of first column vector, what I will do, I will do this x1 minus m1, and I do this for all. Let's say I call it I, m I x I. I do it for all I equal to 0 to n minus 1 if I'm starting from 0. So all n samples, we do the same thing for every column. Okay, so for every column, this will center my data matrix to ensure that each column has mean 0. Every column will have a mean of 0. Now there is a question to standardize or not. To standardize means they mean 0 and standard deviation of unit standard deviation of 1. So if the importance of feature is independent of the variance of the feature, like importance of the feature, if the feature value is important, the value of the feature is important, and it is more important than variance of the feature, then divide each observation in a column by that column's standard deviation. That will make it standardized. So what we are doing over here in these two steps 2 and 3, we are basically standardizing mean of 0 and standard deviation of 1. That is called the centered matrix, centered and standardized matrix. Okay, so centered is obtained by step number 2 and standardized is obtained by point number 3. So this is a subjective judgment. Subjective judgment in the mean that you need to understand whether the importance of the feature value is more important than variance of the feature. Then you don't do it. Then you standardize. Otherwise, you don't need to standardize. Okay. If the importance of features is independent of variance, then you divide each observation in a column by that column's standard deviation. This combined with the step 2 standardizes each column of X to make sure each column has a mean of 0 and a standard deviation 1. Yeah, in case of importance, we mean that how important it is while predicting Y. So if that variable is very important, that without that variable you cannot actually predict Y, then that is what we are talking about, importance of feature. Take the matrix Z and transpose it. Okay, so now we have from X we have obtained matrix Z. Matrix Z is centered and possibly standardized. So if matrix Z is there, we transpose it and then we obtain ZTZ. ZTZ and ZTZ is what we have discussed in previous class also when I was talking about singular value decomposition, that these, when a matrix is multiplied with its transpose, there are several properties. It is symmetric, it is semi-positive definite, positive semi-definite, and it's a covariance matrix also. We get a covariance matrix out of it. So resulting matrix is the covariance matrix of Z up to a constant. So we have a constant multiplied to that covariance matrix, but ZTZ is the covariance matrix with a constant. Constant is actually n minus 1 divided by n minus 1. Calculate the eigenvector and their corresponding eigenvalues for this matrix ZTZ. Remember, ZTZ is symmetric, positive semi-definite matrix. So this is the property I talked about yesterday also. We use Eigen decomposition. We can decompose ZTZ, and why we can use Eigen decomposition over here? Because this is a square matrix. ZTZ is a square matrix. In SVD, we were talking about rectangular matrices also. Here I am talking about a square matrix. And square matrix, how do we obtain a square matrix? ZTZ, this is a square matrix. By its property, it becomes a square matrix. So we are able to find out the perform the Eigen decomposition of this matrix. We can decompose this matrix into three components, P, D, and P transpose, where P is the matrix of eigenvectors and D is a diagonal matrix with eigenvalues on the diagonal and values of 0 everywhere else. So try to find out the correlation, I mean the similarity between the SVD algorithm and PC algorithm. Right. So we perform an Eigen decomposition of this symmetric matrix. Eigen decomposition results in three components, P, D, and P transpose. So of course two components, third one is the transpose of P. But this can be represented as a ZTZ matrix can be represented as P, D, PT, where P is the matrix of eigenvectors. Just so we transform this into this representation PDPT, where P is the matrix of eigenvector. Yesterday also we talked about matrix of eigenvector, and D is a diagonal matrix of eigenvalues. Okay, we will see how do we do that. The eigenvalues on the diagonal D will be associated with the corresponding column P. So we again sorted in the order of decreasing eigenvalue. Okay, that is the first element of D is lambda 1 and the corresponding eigenvector for the first column of P is the first column of P, right? So this holds for all elements in D and their corresponding eigenvectors in P. So we now sort all the eigenvalues in the decreasing order from largest to smallest and call this sorted matrix of eigenvector as P star, right? So we have Z star as no. So you see over here we have this decomposition. First, what we did, we find out the Z T Z. From this matrix, we perform an eigen decomposition with which we are able to find out P D P transpose. When we have P D P transpose, we sort our eigen values into this order of decreasing eigenvalue, decreasing largest to smallest. And when we sort it in this order, largest to smallest, then our vectors of P should also be sorted in the same fashion. And when we sort them, we call them P star. So P star is a matrix of eigenvectors in which the corresponding eigenvalue is sorted from left to right in the decreasing order of magnitude. Now we have P star. This P star could be called a projection direction. This P star is a direction of decreasing importance. Now this P star is the matrix which we multiply to the original matrix will give us a projection of the original matrix onto the new dimensional space. Now this is what we are trying to achieve over here. So we calculate Z star. Z star is a projection. How do we obtain this projection? We multiply the original matrix with P star. This new matrix Z star is a centered standardized version of X, the original data matrix X. But now each observation is a combination of the original values, original variables, where weights are determined by the eigenvector. So when we perform the linear combination weight values are actually determined by the eigenvector. Because our eigenvector in P star are independent and orthogonal to one another, each column of Z star is also linearly independent of one another. Okay, so there is no covariance among these. Finally, we decide how many features to keep versus how many to drop. And this how many to drop, again, there is a method to obtain how many features we want to drop. And using that method, we will identify which feature or how many features we want to drop. Once we have dropped the features which are not important, the transformed variable, the transformed matrix is the matrix with lesser number of dimension, and that is all about principal component analysis. Okay, so what we are doing over here, we have our original data matrix X. First we centered and standardized. Centered means you subtract by mean all the column values, we subtract the mean of that column value. So all the columns are centered, then all columns are divided by its standard deviation. That means it is standardized. Okay, so centered and standardized, or centered or standardized, this is the optional step. So it depends upon what kind of data you have, what is your perception of the data. So a centered and standardized matrix is called matrix Z. We take this matrix Z, and now just like SVD, we perform a decomposition of this matrix. What kind of decomposition we are performing? We are performing an eigen decomposition of this matrix. To perform eigen decomposition, we need a symmetric matrix. So to find out the symmetric matrix, what do? We take matrix Z and we take transpose of matrix Z. We multiply matrix Z with matrix ZT, okay, or ZT with Z, and this becomes a symmetric matrix. Symmetric matrix for which eigen decomposition can be performed. Now we decompose this matrix ZTZ into three components: P, D, and P transpose. And as it says, ZTZ is, if we want to obtain ZTZ back, we perform this multiplication: P multiplied by D multiplied by P transpose, you will get ZTZ. Okay, so you will get this ZTZ, and from this you can obtain the original matrix also. So these steps are equal to each other. Till this time, all the data is preserved. Okay, so data is preserved. Now how do you obtain this decomposition? You need to have two components, first P and then other is D. So three part decomposition. First part is P, second part is D, third part is transpose of the first part, that is P transpose. Now to obtain P, we need to identify the eigenvectors, all the eigenvectors. Okay, you have these eigenvectors of P. Then D is the diagonal matrix of eigenvalues, where we have all the eigenvalues eigenvalue 1, eigenvalue 2, eigenvalue 3, all these eigenvalues on the diagonal, and rest of the elements are 0. Now, if we have these two matrices, then what we do, we take P and sort the columns, because all the columns are eigenvector. Remember, like previously also, all the columns were eigenvectors. So we have all the columns, and every column is an eigenvector. Depending upon the magnitude of eigenvalue, so eigenvalue could be larger, smaller, smaller, smaller. So we sort these eigenvalue in the decreasing order of their magnitude. If we sort these eigenvalues in the decreasing order of their magnitude, we sort the columns of P as well. So this P is also sorted in the order of decreasing magnitude of eigenvalues. We call this special type of P as P star. Okay, we call this as P star. So we sort these eigenvalues in decreasing order, and corresponding vector of P is also sorted, right? The columns of P is also sorted because every column represents a eigenvalue. So this P star becomes an kind of a directional space. P star becomes a direction, and what we do, we multiply P star into Z. When we multiply P star into Z, we are projecting Z onto the new directional space, whole directional space. Why do I call it directional space? Because you see, every vector of P is independent to each other. All of them are eigenvectors. Okay. So, and depending upon magnitude, they specify to us which one is having the maximum variance. So when I multiply Z with P star, I get our projection of data, the original data, and see, Z is the original data with only slight change, that Z is a standardized and centered version of X. Otherwise, all the values are basically of X only. So Z star that we obtain is um, projection of original data onto new directional space, and Z star is standardized and centered version of X. But now each observation is a combination of original variables where weight are determined by eigenvectors. Since eigenvectors are independent and orthogonal to one another, Z star, the columns of Z star are also linearly independent of one another. Then finally, you may decide how many columns to drop, and those columns you can drop. How do you decide? We have some ways to decide how many and which one to drop. Now, there are two methods of actually performing this PCA. The first one is covariance method, and the other is singular value decomposition method. Okay, so again, we take the help of singular value decomposition, and through that we perform PCA. The first method, the covariance method, is unique to PCA. Most of the people follow SVD and covariance depending upon what is their requirement. If you want extremely precise value, because in covariance the transformation loses some, it approximates a bit harder. So if you want more precise transformation, then you go for singular value decomposition. Otherwise, covariance matrix decomposition is also very easy. Let the data matrix A be of n by d size. So I'm again changing the notation because all these notations are found in literature. So once you read this article, there are variations of notation, but you will be able to relate, because previously I was using X, now I'm calling it A, and in singular value decomposition also I called it A. So the idea is same. I'm talking about the data matrix, right? So all the time I'm talking about data matrix, and that is why whatever be the symbol I have used, I have always written the matrix name as data matrix. Okay, so you very well can understand. And many a time seeing these different type of notation helps us, because in literature we study different books, different papers, different blogs, lectures, and everybody uses their own notation. So a different set of notations are available, prevailing in literature. So with this you can get a fair idea, as soon as you see some kind of picture in which C equal to 80 upon n minus 1, you will be immediately able to relate to this lecture that okay, this was discussed and I have read this, so I understand very thoroughly what does it mean by C, what does it mean by A or N, or etc. So our data matrix is I call it A, has n by d size. N by d size means normally we say that our data has d dimension, so number of columns is d, and I have got n samples, so number of rows is n, so n by d size, where n is number of samples and d is number of variables. Let us assume that it is centered. So of course the first step is centering of the data, in which we take mean and subtract mean value from each value of the column. Column mean have been subtracted and now are equal to 0. Then d by d covariance matrix C is given by ATA upon n minus 1. You remember when I said that ZTZ is a covariance matrix? ZTZ is a covariance matrix up to a constant. Okay, so this is the constant n minus 1. It is divided by n minus 1, and this is the exact form of a covariance matrix. In matrix form, the empirical covariance matrix of the original variable can be written as V lambda V transpose. Okay. So when we have V lambda V transpose, where V is the matrix of eigenvector and each column is an eigenvector. Lambda is a diagonal matrix with eigenvalue lambda I in the decreasing order of diagonal. These eigenvectors are called principal axis or principal direction of the data, because ultimately what we are doing, when we have these vectors, in those vectors only I am actually projecting the data. Projection of data on the principal axis are called principal component, or also called as PC score, principal component score. So remember, there are few terms which are defined over here. Listen to it very carefully and with patience. Eigenvectors are called principal axis or principal direction of the data. Okay, so when we obtain eigenvector, what we are obtaining are the directions. We are obtaining the direction. Then the data is projected in those directions. When data is projected in those directions, the data assumes new value. When data assumes new value, these values are called principal components. The eigenvectors are not called principal component, but the data value, which is a result of projection of our original data into new direction, is called the principal component. So eigenvector are principal axis or principal direction of the data. Okay, so like in this case, you see two examples I have. One is the original data x1 and x2. X1 and x2 were having this directional space. X1 is in this direction, x2 is in vertical direction, x1 horizontal. When original data was plotted, then we obtained the data points as plotted, visualized like this. Okay, then we found out two directions: direction of this long line, long arrow, and direction of this shorter arrow. Now these are two directions. When I say what are direction are basically the eigenvector. The eigenvector with the maximum eigenvalue is this line. Now this is again a direction. Okay, the second principal component is the eigenvector. No, second principal component is obtained by the direction of the second eigenvector. So second eigenvector gives us the second direction, and second eigenvector will have the second biggest eigenvalue. Okay, so I obtained two directions. First direction in the direction given by first eigenvector, second direction in the direction given by second eigenvector. Now all the data points, whatever data point I would have, ultimately these are all data points, right? I will obtain these data points. These are the data points from here to here, here, here. All these data points are spread like this. Spread like this. There will be data points here also. So my data points are spread like this, and this spread was courtesy to x1 and x2 because of these two, right? These two directions. Now I have obtained two new direction, and I want to project these points onto new direction. Okay. So when I project these onto these two direction, what will it be? It will be a linear combination of x1 and x2, because this point, if I take this point, this is a representation of some value of x1 and some value of x2, but I am projecting it onto this axis. This is the direction. Okay, this is the direction. Take a line. This is the direction in which I am projecting it. So if I have to project I will multiply the vector of first eigenvector with this value, and it will project it over there. And when it projects, the scenario becomes something like this. You have the original data, and in original data, x-axis in this direction, y-axis in this direction. But then you understand that your principal component will be somewhere in this direction, because this is the maximum variance. Okay. Now, after performing principal component, your data should again be shifted such that now this is PC1. You see, earlier it was like a slant. Okay. There, this line, that line you can draw. So in original dimensional space, the original dimensional space you have, this data was can be drawn in this direction. However, when you change the dimension, how we are changing the dimension? We are projecting our data onto those directions of eigenvector. So after this, now new coordinate axis is created, in which the x-axis, you see, becomes principal component 1, the principal direction of maximum variance. This becomes the first direction. Then PC2, this gives the second direction. This one, this green one. So very small variation in these two directions. Okay, and now so original data, this data is projected onto this kind of axis. So instead of x and y, now the columns will be called PC1 and PC2. Okay. So eigenvectors are the principal axis or principal direction of the data. Projection of original data on principal axis are called principal component. This can be seen as the new transformed variable. So we now have every column as one of the principal component. When you multiply your Z matrix to P star, you get a new matrix. A new matrix will have each column as one principal component. And principal component is, again, in the new matrix, when you have it, is a feature. It is treated as a feature. But this feature will not be similar to the previous feature. Every feature is a linear combination of your original feature. The jth principal component is given by jth column of AV. Okay, so you have A, and that is multiplied by V. V is again the P star. You see the P star over here. So A is we see that A is centered and standardized. It is centered. Yeah, let's assume it is centered. So A is somewhat like Z, and V is somewhat like P star. So the jth principal component given by jth column of AV. The coordinate of ith data point in the new PC space are given by ith row of AV. Okay. So number of rows will remain same, but number of columns will be changed. The second way of performing principal component analysis is SVD, in which we take the help of singular value decomposition method that we had studied previously. Now let's see how do we do that. We perform a singular value decomposition of A, and to do that, again, U sigma V star V transpose, right? We obtain a decomposition. A is decomposed into V sigma V transpose, U sigma V transpose, sorry. So U is a unitary matrix, sigma is a diagonal matrix of singular values Si. From 1 and 3, we have 1 over here and 3 over here. You see, if I have okay, So what we are doing over here, we substitute this term A, we take this term A and put it over here in equation 1. So in place of A, I will put U sigma V transpose and again find transpose of it. And then second A again, I'll substitute U sigma V transpose. So let's see what happens. When I do that, 1 by n minus 1 is taken common, then A transpose A, which is substituted by U sigma V transpose and U sigma V transpose. Now we expanded, when we expand this U sigma V transpose, take transpose of it, it becomes V sigma U transpose, and then ultimately this remains same. When we open it, we multiply U transpose U will become identity, because remember previously also we had found that U and V are orthogonal matrices. So their U transpose U becomes identity matrix. So this will become identity matrix by the property of decomposition of SVD. In SVD itself, we had found out these properties. So as per the property of U and V, U transpose U will be identity matrix. So that becomes identity. Now sigma and sigma multiplied will become sigma square. So we have C equal to V sigma square upon n minus 1 V transpose, which is, you see, very similar to the term this V lambda V transpose. Okay, V, if I could call this term lambda, like here I have called it lambda. So this term, the middle term is treated as lambda and the third term is V transpose. Okay, so it is basically again back to this format where I had started. I had started at the point where I was talking about I had this definition somewhere, right? PDP transpose. Yeah. So we decomposed into PDP transpose. In this notation, we decomposed into V lambda V transpose, and the same we obtained over here. The C is V lambda V transpose, where lambda could be represented by the middle term. So lambda equal to sigma square upon n minus 1. If we could obtain singular values as well, and we find out from singular value decomposition, we have sigma as the matrix of singular values. So take a square of it and divide it by n minus 1, you will get the lambda matrix. Since both lambda and sigma are diagonal matrices, we can infer the relation between individual elements of lambda, that is eigenvalue, and sigma, that is singular values, as lambda I equal to square of singular values divided by n minus 1. The principal components are given by A multiplied by V, that is equal to U sigma V transpose V equal to U sigma. So either it is AV or U sigma, this is basically same. And remember, when I was talking about singular value decomposition, there also we talked about two transformation. One was AV and the other was U sigma. Okay, the AV or U sigma both are same. So in terms of singular value decomposition or in terms of covariance method, both ways you can perform the principal component analysis. So to summarize this method, let us make a revision of what are the steps we performed. First, we have a matrix A. This matrix is the original data matrix. We perform a decomposition using the singular value decomposition, and we decompose it into three parts: U, sigma, V transpose. Then columns of V are principal, direction, or axis. Okay. Columns of U sigma are principal component, the score. So either you say AV or U sigma, both are principal component or score. Columns of V are principal, direction, or axis. So columns of V are the direction. When we multiply V with A, the original data matrix, that gives us the principal component. So AV gives us the principal component. AV is same as U sigma, because you see, if you replace A in this equation AV, if you replace A, what was A? A is U sigma BT, right? So you put U sigma BT over here, BT and V become identity. So ultimately you get U sigma. So when you can decompose it, the columns of V give you the principal direction. When you multiply principal direction to original matrix, you get principal component. Singular values are related to eigenvalues of covariance metric as lambda I equal to Si square upon n minus 1. Each eigenvalue lambda I show variances of respective principal component. Okay, how much variance that principal component demonstrates. The standardized score are given by columns of underscore n minus 1 u underscore n minus 1 u, and loading are given by the columns of v sigma upon underscore n minus 1. Okay, the above is correct only if A is centered. Only then it is then the covariance matrix equal to ATA upon n minus 1. So that is one condition with which we actually started, that our data matrix should be centered, right? So if it is centered, then only the standardized scores of columns is given by this and loadings are given by column of this. The above is correct only for A having samples in rows and variables in column, and that is why again at the very beginning I talked about that we need a matrix, data matrix, in which the data is stored in the form of rows and columns. If variables are in rows and column and samples in column, then U and V exchange interpretation. Okay, so feature should be in column and rows should represent the data point. If it is other way around, then U and V exchange their interpretation. If one wants to perform PC on a correlation matrix instead of covariance matrix, then column of A should not only be centered but standardized as well. Okay. To reduce the dimensionality of the data from D dimension to K dimension, where K is less than D, select first K columns of U. So ultimately we have the U matrix and we are going to multiply it with sigma. So select columns of U. You can say columns of U or columns of V, first K columns. Okay. First K columns of U or first K columns of V, and K by K upper left part of sigma. If you are using U, then you have to multiply it with sigma. Their product UK sigma K is the required N by K matrix containing first K principal components. Okay. We will see how do we find out K. Further multiplying by first K principal components by the corresponding principal axis Vk yields your matrix AK. Matrix that has the original n by d size, but it is of lower rank. This matrix AK provides a reconstruction of the original data from the K principal component. It has the lowest possible reconstruction error. So when you use the method of singular value decomposition, then the reconstruction error that you obtain is minimum. Strictly speaking, U is of n by n size and V is of d by d size. However, n is greater than d. If n is greater than d, then last n minus d columns of U are arbitrary and corresponding rows of sigma are constant zeros. Okay. One should therefore use economy size of or thin SVD, then return U of n by d size, dropping the useless columns. For large n, in which n is much greater than d, matrix U would otherwise be unnecessarily used. So you understand, when we were doing U sigma V previously, we were actually putting a lot of zeros over here. So we had U and we had sigma and we had V transpose in the SVD, and when we were creating sigma, we were actually saying that sigma should be created in the fashion that sigma would be over here, then a lot of columns with 0 0 0 0 0 0 need to be created such that the U matrix, suppose it is n by n, and V matrix, V transpose matrix, which was d by d, we need to match it such that this will be n by d. This matrix will become n by d. So to match it with ND unnecessary, we need to add so many columns. Okay. And if this D reduces to K, so I will have K by K, and K is definitely smaller than D. So what I'm doing is I'm having so many row by column. So number of rows of this should match the number of columns of this. Okay. So I should reduce the number of rows in U such that I don't end up with useless columns which are not at all required. Okay, unnecessary putting so many zeros. So you will take only those many U's which are important to us. So that is what we are saying over here. We use an economy size thin SVD. Okay. So, however, if n is greater than d, then last n minus d columns of U are arbitrary and corresponding rows of sigma are constant 0. So, we should reduce this. These columns should be dropped, dropping the useless columns. Okay. Now, when we perform PCA through scikit-learn API, the scikit-learn API library provides PCA class that can fit on dataset and used to perform a training dataset and any additional dataset. So you see, these are the steps. We first have the data. We define the transform PCA equal to. We call the transform. We create an object from this PCA class. We prepare the transform on dataset. So PCA dot fit. We fit our data. So basically, we are finding out our directions over here. Okay. After we find out our direction, we perform transform. So our data is transformed in those directions. So first we call the PCA object. Okay, so PCA method will be initialized. We call the PCA method on the data, so we find out directions. What direction? The directions of eigenvectors, and then through those eigenvector we transform our data in the PCA dot transform data line. Output of PCA can be used as input to train a model. Perhaps the best approach is to use a pipeline where first step is PCA transform and the next step is learning algorithm that takes the transform data. So what do? We perform this pipeline. So first we perform PCA and then we perform logistic regression where M is the output. It can also be a good idea to normalize data prior to performing PCA, and that can also be part of your pipeline. So if you are normalizing, what do? First you perform the normalization, then you perform the PCA, and then with the output of that, you perform the logistic regression. Now, in a worked example, let's see what we are doing over here. Suppose we have a data set of 1000 samples and 20 features, and we have 1000 target variables. Okay. And how do we create this data? Number of samples equal to 1000, number of features equal to 20. Number of informative feature is 15 and 5 are redundant features. So this using the make classification function defined in scikit-learn, we can create a random data set. Okay. So this is the shape of this data set, and in this you see a number of informative features have been selected to be 15 and redundant features 5. So ultimately 15 are the features to which I want to reduce my data set. We can use dimensionality reduction on this data set while fitting a logistic regression model. We will use a pipeline where the first step performs PCA, selects the 10 most important dimensions or component, then fits a logistic regression model on these features. We don't need to normalize the variable on this data set as all variables have the same scale by design. So this is as per the design itself that they have same scale. The pipeline will be evaluated using repeated stratified cross validation with 3 steps of 10-fold per repeat. Okay. So you see we are doing it over here. So what we do over here, we make classification, we create the data sample, then we define the pipeline and steps of this pipeline. And first we perform PCA by calling these, and number of components we have specified to be 10. So only 10 eigenvectors will be chosen, and then we perform the logistic regression. We call this pipeline, perform these steps, and then after this we perform repeated stratified k-fold cross validation. Okay. So our accuracy has come out to be 81%, and mean accuracy 81%, standard deviation is 3%. Now, how do we know that reducing 20 dimension of input down to 10 is good or the best that we can do? Okay, so these are the practical implications. So we understood the theory of principal component analysis, and while doing the practical implementation, you also have to make this decision how many principal component you want to retain. In this example, although we have taken number of informative features to be 10, we used only 10 components. Number of informative features to be 15, but we have taken only 10. So how do we know whether 10 is sufficient or not? So we can make an arbitrary. Okay. So we don't, in this case, 10 was an arbitrary choice. A better approach is to evaluate the same transform and model with different number of input feature and choose the number of features that result in the best average performance. So we do a repeated running. We do with 1, 2, 3, 4, 5 up to 15, and we see when the accuracy is reaching a plateau. Okay. So like this one, this example performs it, and you see when I run this example. So number of features, 1, we gave 54% accuracy, 2 features 71%, 3, 4, 5, 6, 7, accuracy is still increasing, 10 accuracy is increasing, then 81%, 81%, 81%, 81%, up to 14 we got 85%, and 15 86%, and after 15 we are not getting any increase, any change in the accuracy, 86% remains constant. So we can very well judge that last 5 features are not at all useful. Okay. So if we take 15 principal components, 15 principal components will be best. After 15 principal component, we are not getting any increase in the accuracy, so we can safely reduce this principal component number to be 15 instead of 20. We see a general trend of increased performance as the number of dimensions is increased. On this data set, the result suggests a trade-off in the number of dimension versus the classification accuracy of the model. We don't see any improvement beyond 15 component. This matches our definition of the problem, where only the first 15 component contains information about the class and remaining 5 are redundant. So in this example, when we created our classification example, what we had given, number of informative features were 15, number of redundant features were 5. So that also matches the creation of data itself. We may choose to use a PCA transform and logistic regression model combination as our final model. This involves putting the pipeline on all available data and using the pipeline to make prediction on new data. The same transform must be performed on this new data, which is handled automatically by the pipeline. So if you see this pipeline, you see what is happening. First, we make this data, then we define the pipeline. PCA first and then logistic regression second, and this pipeline involves all these steps. When we fit the data, make a single prediction. Okay, so class prediction is happening over here. So running the example fits the pipeline on all available data and makes a prediction on new data. Here the transform uses 15 most important components from the PCA transform, as we found from testing above. The new row of data with 20 columns is provided and is automatically transformed to 15 component and fed to logistic regression model in order to predict the class level. Okay, so what is happening over here is that you see, while training while creating the logistic regression model, we had created this pipeline, and this pipeline involved the steps like first PCA will be performed and then logistic regression will be performed. Now, at the time of prediction, at the time of testing, this is a single row of data that is being fed. It has got 20 features. So when you have the testing data has not been taken through the principal component analysis step, PCA step. So you cannot directly feed the testing data into your model for testing, because the training data that it has seen is different. It has seen a training data that had a PCA component only and only 15 features, right? It has not seen the original data. So when the training data has not been the original data, the model that is trained on PCA data, not the original data. So how can you feed original format of data to this model? Okay, that cannot happen. So in that case, when you perform the prediction should also be performed on the model which has been created using the pipeline. So this pipeline still exists at the time of prediction also. So when you perform this predict, and you pass this row of original test data to this, what happens is that first it goes through PCA. First, this data will be projected onto the new principal component direction, and then out of those 20, only 15 will be taken, and those 15 will be tested upon, right? So in this case, this is prediction is happening, but the core concept to mention over here is that the test data also goes through the PCA step. It goes through PCA step. This data gets projected onto principal component axis, principal component directions, and then the principal component values are obtained. Out of 20 principal component values, only 15 are taken, and with those 15 the prediction is performed, the logistic regression classification is performed, and that results in a class, whichever class that might be. Now, in this example, I actually talk about how do we decide. Like over here, we were very sure that okay, we have 15 components which are useful, 15 components which are useful, and rest of them are redundant. And we showed you in this order that you perform this uh, accuracy test and see which all are useful and which are not useful. But you see in this scenario, what is happening is that many a times this doesn't help, because you will have to run each and every accuracy test, and this takes too much time. So how do we decide upon which PCA to drop? There are different ways of performing it. Like in this, we perform a proportion of variance explained. So we try to find out the variance obtained by principal component, and then depending upon that, we decide which how many principal components to draw. So there are three methods defined in literature. First one is arbitrary select, how many dimensions we want to keep, which is not a very scientific method. Calculate the proportion of variance explained. For each feature, pick a threshold and add feature until you hit that threshold. For example, if you want to explain 80% of total variability possibly explained by your model, add feature with the largest explained proportion of variance until your proportion of variance explained hits or exceeds 80%. Like in this example, I have given it. Yeah, proportion of variance explained. You see, in this example, in PC, variance means summative variance or multivariance variability or overall variability or total variability. Okay, so when I talk about variance, it means multivariate variability or overall variability or total variability, whatever be the names that you most understand. This variance is talking about that total variability. Now below is the covariance metric of some three variables. So we have three variables, 1, 2, 3, and we obtain the covariance matrix. Like their variances are on the diagonal, and sum of three values is the overall variability. So you see, this is the matrix. Okay, these are the columns of there are three variables, 1, 2, 3, and for these I'm going to find out the covariance matrix. Now PCA replaces original variable with new variable. Okay, no, sorry. This is the covariance matrix. Okay, or some three variables. The variables are not given. These are the covariance. This is the covariance matrix. So you see, this value, let's say, value this and this is the covariance between first and second variable. So ultimately, first and second, these two are same. This is first and third, and this is first and third. So again, these values are same. So this is what is happening, and so this is a covariance matrix, and when we perform PCA, what we do is that original variable are transformed into the covariance of these values, covariance of the eigenvectors. Okay, covariance of the eigenvector. So as we have already seen, that all the eigenvectors are perpendicular to each other, so their covariance is zero. They are linearly independent of each other. So if the covariance is zero, that is why we obtain the non-diagonal values as zero. Okay. However, these values are the values which are variance of the variance explained by the eigenvector. So first eigenvector is the first column, and it has a variance of 1.6513 something something. Now you see, this is the biggest value. 1.65 is the biggest value. 1.65 has the biggest value, and then second one has the next biggest value, third one has the next biggest value, and this is the only left one. So you see, PCA replaces the original variable with new variable called principal component. And these principal components are orthogonal. They have zero covariance. So there is no covariance between first column and second column. That is why the first column, this value is zero and this value is zero. First column versus third column, again zero. So this is zero and this is zero. Okay. So the non-diagonal elements are zero because this is again a covariance matrix of principal components, right? So the covariance matrix between the principal component extracted from above data is this. This is the covariance matrix of the principal component. Note that diagonal sum is still 3.448. When I obtain the variance on the diagonal sum of three values is 3.448. So if you add 1.34, 0.61 and 1.43, you will obtain a value of 3.448. The same 3.448 variance is again obtained by the principal component covariance matrix. The diagonal sum is still 3.448, which says that all three components account for all the multivariate variability. So whatever be the multivariate variability of original data is preserved by the three principal components, because ultimately there were three features in the original data and three features are there in the transformed data. So there is no reduction in number of dimensions. So three dimensions were there previously, three dimension in this also. So since we are not reducing the dimension, we are not approximating, and total variability is defined. Okay. So total variability is 3.448. The first principal component accounts for or explains. So remember, I have always been talking about variance explained, and this is the term that I actually refer to. How much of total variance is explained by first principal component? This is first principal component. How much is the variance? 1.6513. So I take 1.6513 divided by 3.4 divided by total, and how much percentage that is? That is 47.9%. So first principal component explains 47.9% of the total variability of the total overall variability of original data. So first principal component accounts for the total spread of the 47% of total variability is explained by first principal component. Now let us see how much the second principal component explains. 1.22 divided by total variability. So 1.22 divided by 3.48 is equal to 35.4% variability. Overall variability is explained by the second one. When you add these two together, how much do you get? Of course, it is more than 80%. So it says that if you add, if your target is, let's say this example was given, the second example, suppose you want 80% of total variability explained. So you take first principal component and second principal component. With first and second, this is 47%, this is 35%. I think it will give you more than 80%, right? So what do they mean when they say that PCA maximizes variance? PCA explains maximal variance. That is not, of course, that it finds the largest variance among three values. PCA finds in the data space the dimension or the direction with the largest variance out of overall variance. Out of these three variances, it finds out the direction of largest variance. That largest variance would be 1.65, and that direction, the variance in that direction is 1.65. Then it finds the dimension of the second largest variance, which is of course orthogonal to the first one, and then the second dimension would be 1.22 variance, and so on. Okay, and this goes on like that. So first principal component is finds the direction and then projection of original data in that direction. Second principal component finds the direction of remaining maximum variance and then projection of data on that direction, and so on. So this is the second method. The third method to calculate or find out which PC to drop is actually the plot of cumulative proportion of variance explained. So in this is also another example which is explained in literature. Calculate the proportion of variance explained for each feature. Sort features by proportions of variance explained and plot the cumulative proportion graph as you keep more features. Okay, this plot is called scree plot. One can pick how many features to include by identifying the plot where next feature has a significant drop in variance explained related to previous feature and choosing the features up until that point. So you see over here we have proportions of variance explained in this on the y-axis, and on x-axis we have PC1, PC2. You keep on adding. Okay, cumulative variance is adding like this, but you see after adding PC1, PC2, after adding PC2, I get a very substantial decrease in the variance of proportion of variance explained. So wherever you find an elbow, that is the portion where you should stop. Okay. So red line indicates the proportion of variance explained by each feature, which is calculated by taking the principal component's eigenvalue divided by sum of all eigenvalues. So what is happening over here? The proportions of variance explained by including only principal component 1 is lambda 1 upon sum of all lambda, which is 23%. Then second is about 19%. Third is about first and 2 when added gives us 42%. This is where the yellow line comes in. Okay, this one. The yellow line indicates the cumulative proportion of variance explained if you include all principal component up to that point, right? So these are the methods. These are the three methods with which you can decide which principal component to drop and which principal component to keep. However, among these, there are several methods applied by everyone depending upon the problem. See, this is also one of the way in which you can actually check. So you'll have to predict, evaluate the model for with each and every feature, each and every principal component. Now, you can say that since we have sorted the principal component in the decreasing order of their magnitude, the first principal component will give you the biggest rise in the accuracy. Second principal component will give you slightly more rise, but not as big as the first one. So you see the increase in accuracy with the first one. Of course it started from 0, so the first one gave you 54% accuracy. Second one gave you 71, means there is a difference of almost 17% increase. 17% increase. First one gives you 54% increase. Second one gives you 17% increase. Third one gives you almost 1% increase. So the level of increase decreases. Okay, the level with which the increase happens, that decreases, but ultimately with this you can choose when your accuracy is not at all increasing, then you can stop over here. But in bigger models, bigger data point, this might not be always possible. Okay, so what you do is we try to find out the variance explained, and for this we don't really need to run our model. Okay, to identify the proportion of variance explained, I don't really need to run the model again and again for so many times, as many principal component as many times. What I need to do, I need to find out the variance, and then I need to find out the variance explained. So how much variance explained you want to obtain, fix that value, that becomes a hyperparameter for which you have to identify a value and try to achieve that target. Okay, so that is all from my side, and I am open for questions. If you have any questions, probably we can take those questions. Can we have questions, please? No questions? I hope principal component analysis was clear, because you see, this all is very closely related to the linear algebra and how we are dealing with vectors and vector space. Okay, so once you have a concept of vector and vector space, then it becomes much clearer to understand what type of data we have and how we are projecting in another dimension. So I hope it is clear to you, and all of it happens with the concept of eigenvector and eigenvalues. So eigenvector and eigenvalue concept is very important over here. With the mathematical understanding, I hope if I could give you an example of one of the lectures I have found over internet, which very clearly and very beautifully explains. One blue, one brown, one blue, three brown, I suppose. One blue, three brown. Yeah, YouTube video of, and there they explain eigenvalues. Just a second, let me share this. Okay, so I'll share this link over here. This is a video of YouTuber, three blue, one brown, and he runs a series on mathematics, linear algebra, then and other topics as well, like deep learning as well, neural network as well, and basically he has a very thorough series on algebra, essence of linear algebra. So if you look at this video, you will find very clear-cut understanding with a lot of visualizations, what are eigenvalues, what are eigenvector, and you will get a very beautiful understanding. What does it really mean by understanding the eigenvector, and what do they do? So when we have eigenvector, we are actually getting the direction of these principal components. And when we have the direction, we can project our data onto those direction, and that becomes the principal component or principal scores. So basically our data, original data, is being projected onto a new dimensional space, new coordinate system, new space. And new, why we are doing it? Because after projecting, we get this facility that we can drop some of the directions. And what are directions? Directions are nothing but dimensions. So in original data, we were not able to drop these dimensions because we were not clear about how important these dimensions are. But when you project your data onto the principal axis, then you get a very clear understanding that which is important, which is not. You retain which is important and you discard which is not important. So when you discard, of course, you are discarding some of the dimensions, and that actually is the dimensionality reduction. What is the fundamental basis with which we identify which is important, which is not? Again, the value of eigenvector, the percentage of variance explained, or as per this key script plot. So basically, you take the accuracy chart, how much is the accuracy, how much is the increase in accuracy, one way, or you utilize this method of how much of percentage of variance is being explained by how many principal component. And if you are satisfied with variance explained, percentage of variance explained, discard the remaining one. So these are the methods of obtaining principal component, and these are the methods of finding out how many principal components to keep. I hope it is clear, and if you have any question, probably you can ask me. My email ID is munindra@IIITA.ac.in. So you can always email me, and you can ask me any question. Being coordinator of this FDP, co-coordinator with Dr. Vivek Tiwari, I also have the responsibility that all the doubts of every participant are clarified, and I'll be happy to interact with you. So if there's nothing more, probably I will end the session at this point. And I thank you all for attending the session, being a patient listener, and thank you for your patience as well. Okay, thanks a lot, and all the best for the quiz today. Okay, bye.
Vivek sir. Good morning, Vivek sir.